Hello! I'm going to do a difficult force problem. So we have an objective about being able to solve hard force problems, difficult force problems. Many of them involve two different objects that are connected somehow. So this is going to be a two-object force problem where the two objects are connected, and we'll see how that connection affects the acceleration, the movement of both of them. Our problem today. Two blocks hang from opposite ends of a rope, and the rope passes over a pair of pulleys. One block has a weight of 412 newtons, and the other has a weight of 908 newtons. The rope and the pulleys are massless, and there's no friction. What is the acceleration of the lighter block? All right, so typical process, draw our picture. So we've got two blocks hanging on opposite ends of the rope, and the rope goes over two pulleys. So, I don't know, something like that. We have one block with a weight of, so let's call this number 1, 412 newtons. And number 2 has a weight of 908 newtons. No mass here, no friction. We want to know what is the acceleration of the lighter block. So acceleration of number 1. Okay, we have our picture. We have our two single knowns. Yeah, great. And we have our unknown. What are we looking for? We're looking for the acceleration of the lighter block. All right, next in our process is usually to figure out the object of interest. Here we have two objects, which means that we're probably going to want to do two different force diagrams. We're going to do one for the first object, a separate, totally separated one for object number 2. So let's give that a try. For object number 1, the 412 Newton weight block, what forces are acting on this thing? Well, the rope is pulling up on it, so we have a tension upwards. The force of gravity, the earth pulling down on it, so we've got tension up, we've got weight down. I'm going to mark that this is M1. We have two different masses here, two different weights, so I got to keep track of that. And well, that's it. So that was pretty simple. How about for number 2? Number 2, here we go. Okay, so earth pulls down on it. This is the weight of the second block, and look at that. We have a tension going up. Very exciting, isn't it? Well, what's next? All right, let's figure out some coordinate systems, and we do our coordinate system along the direction of acceleration. Which way are these things accelerating? Well, this one, it's the light one, so that thing's going up. This thing is going down, which means we want our standard coordinate system. Plus y plus x. Okay, and now we're going to do Newton's second law for both of these. Well, we don't have to worry about the x coordinates, so my xy table for number 1, there's nothing here. All of the y forces. I have a positive tension, a negative m1g. Whee! And look at that, it's identical for number 2. Positive tension, negative m2g. Tension up, weight down, that's what we've got. Both of these are accelerating, both of them are unbalanced. So when we have unbalanced forces, that's when we add up all the forces and set it equal to ma. What do we have here? T minus m, so we have a positive t minus m1g equals ma. Now keep track, this is object number 1, so this is mass number 1 that we're talking about. Here we go, plus t minus m2g equals m2a. You might stop and say, well, that's identical. So isn't this just going to say that, isn't everything going to cancel out? Because these equations are absolutely identical. If I solve this one for t and this one for t, put them together, everything just kind of drops out except masses? We have to take into account something special when we have connected objects. We have to think about the direction of the accelerations. And there's a couple ways you can do this. You can say this is acceleration of number 1 and this is acceleration of number 2. If you do that, we need to do this. Are these two accelerations related? Well, since the objects are tied together, they'd better be moving at the same acceleration. They have the same motion, so their velocity is the same, acceleration is the same, and they've got the same motion. which means that the number for A1 is the same as the number for A2, the absolute value, but the signs are different. A1 is going up, A2 is going down, which means that A1 is negative A2. So if you do it like this and pop in A1 and A2, you'll say, oh, A1 is negative A2. Well, that means this side becomes a negative M2, oops, M1, M1A2. Hard to keep track. So that's one way to do it. And just say, well, they have the same number but opposite directions. The other way to do it is to just look at your force diagram and say, positive tension, negative weight. My acceleration is going up, it's a positive value. So this is a positive value, and then in this case, I don't need the A1 because I know the numbers are the same. So if I do it like this, then I come over here and I say positive tension, negative weight, but the acceleration is downward. I can just put a negative sign in front of it, and I don't have to worry about the A1s and A2s. Both ways are perfectly fine. If you want to make the explicit connection here and then do the replacement, or you can just look and say, well, that's a negative acceleration. I'm just going to make that negative right there. Both are fine. So we have these two equations, and we want to know what is the acceleration of the lighter block. Well, it's going to be the same as the acceleration of the heavier block. What is that? So we want to know acceleration. What do we know? Okay, so I don't know tension. I know mass, gravity, mass. I'm looking for that. Don't know tension. I know mass, gravity, mass, and I'm looking for this. We do know, because this is one string, because the string is there, that string has to have the same tension everywhere. So whatever the tension is in the string here has to be the same as the tension in the string here. This tension and this tension are the same. That's why I didn't bother labeling it T1 and T2. If it's the same string, that tension is the same everywhere. So this is the same as this, which means I can connect these two equations together by putting them both into the form of T equals and setting them equal. So if I do this one, M1G plus M1A, bring that over. Here, bring that over. T equals M2G minus M2A. Our equations are no longer exactly similar. So what I just said is that the tension has to equal the tension. So let's replace this one with the left-hand one, M1G plus M1A equals this tension, M2G minus M2A. All right, at this point, I have an equation which has acceleration in it, which is what I'm looking for, and no other unknowns. This is it. How do I solve it? How do I get the acceleration out of here? Well, I need to get all the terms with acceleration over to one side, everything without acceleration to the other side. So A terms here, non-A terms over there. I've got an M1A here. I'm going to bring this M2A over to the other side. It becomes a positive. And then I've got that term over here, and this one needs to go over. It becomes a negative. All right, how does this help me? I can factor out the A. M1 plus M2 equals M2G minus M1G, and here divide both sides by this term. So what I end up with is M2G, the weight of the second one, minus the weight of the first one, over the combined masses. Be careful, I'm talking about masses and weights here. So here is an equation for the acceleration with known values. So it's weight 1 minus weight 2 over the combined mass. I don't know my masses, right? I was given weights. So let's go way back here and figure out what my actual masses are. Usually I give you a mass and you have to calculate the weight mg. Here I'm giving you weights and asking, hey, now you have to calculate the mass. So if the weight is 412 newtons and weight is mass times gravity, so mg equals 412 newtons, then my mass is going to be 412 newtons divided by 9.8 meters per second squared. So m1 is 42.0 kilograms. Do the same thing for the second mass and you'll get something weird. What was that? 92.7? 92.7 kilograms. We have our masses, we have our gravity, we can solve for the acceleration. So if you do that, you get an acceleration of 3.8 meters per second squared. And I'm not putting a direction on that because the direction is different. This one's accelerating up, this one's accelerating down. So the value of the acceleration is 3.8. And if I were to say, well, actually the question says, what is the acceleration of the lighter block? So to actually answer the question, the true answer is the acceleration of block 1 is 3.8 meters per second squared upward. That's the total answer for that part. So here's a two-object problem, and we have to take into account the connection between the two objects. This is a single string, a single rope, which means the tension has to be the same everywhere. And we have to take into account the difference in the direction of the acceleration in order to make this work. The most common mistake people make when they're doing these kind of problems is losing track of that negative, well, this negative right here. That is the most common mistake. So always make sure you are thinking about the direction of the acceleration when you're solving these. It's very, very important. So that's kind of the first part of the problem. Now I have part 2. Suppose the 908 Newton block is removed and you pull down on this rope with a force of 908 newtons. Find the acceleration of the lighter block again. All right, so what are we doing this time? We are removing that weight. So we're removing the physical weight, and now we are going to, actually, how much do I need to erase? I'm thinking about this. Now we're going to pull down on it with a force of 908 newtons. So it looks like this. So we're pulling, how do you draw pulling down? There. So we're pulling down on it with a force of 908 newtons. So we have that same number. We still want to know, as before, what is the acceleration of the lighter block. Okay, right now, make a prediction about what you think that answer is going to be. When it was 412 and 908 blocks, we got an acceleration of 3.8 meters per second squared. So stop right here and say, is it going to be less than that, equal to that, more than that? Stop. Okay, make your prediction. Hope so. Let's go do the math again. Okay, so what can I get rid of? What can I get rid of? We are pulling down on the rope, and, well, this one doesn't change, right? This one still has the tension of the rope pulling up on it, this one, the weight, earth pulling down, and it's going to accelerate up. This one, well, there's no object anymore. There is no object for us to do a diagram of. So how do we make this work? If we don't have a second object, what is this telling us? So what information are we given by the fact that we're pulling down with a force of 908 newtons? Okay, so stop and think about it. What does that 908 newtons represent? It matches a variable that we already have here. Can you figure out which one? We're pulling on the rope with 908 newtons of pull. That means we're exerting a tension in the rope of 908 newtons. This is now directly our tension. We don't need to do any more math for object 2 because there is no object 2. So you can just say, oh, if we're pulling down on it with a force of 902 newtons, that is my tension. I have a tension equal to 902 newtons. Can I solve for the acceleration? This is all still true, right? We haven't changed anything here. So I know my tension is 908 newtons, excuse me. And I want to solve for the acceleration. Okay, so I have plus tension minus m1g equals m1a. Is that positive or negative? Positive acceleration. I'm looking for that. I know that. I know that. That. This one's very easy. So solve this for the acceleration of block 1, and we get tension minus m1g all over m1. And if you do that math, 908 minus 412 divided by 42, you should get 11.8, so about 12 meters per second squared, upward. That's our answer for part 2. Is that what you predicted? Most people looking at that would say the acceleration should be the same as before. Why isn't it? How can this have a different acceleration when we had 908 newtons hanging on this thing before, and now we're pulling on it with 908 newtons? So let's go back to the first problem, the first part. We have equations for the tension. Let's see what the tension is in the first part of this problem. We already know our acceleration is 3.8, so we know everything. We have 2 different equations for tension, so pick one, solve for t, and then what I like to do is solve the other one for t and make sure that they're about the same, just like we did with 2-object kinematics, where you solve for the time and then you can double check that they end up in the same place. Let's just double check. We have 2 equations for tension. Let's see if they come out the same. And if you do that math, they're not exactly the same, but they're both around 560, 570. So the tension ended up being about 560 or 570 newtons for the first one, where we had a block hanging here. That's a lot less, isn't it, than the tension being 908. So there's more tension on the rope. There's a stronger force pulling up on this thing, which means it's going to go faster. So if the tension was 560 some before, it's going to accelerate at a certain rate. This hasn't changed. Now we increase this to not quite double, much bigger. It's going to accelerate a lot faster. That is why we have different accelerations, because the tension in this situation is not equal to the weight. We get so used to the equilibrium situation where we have tension up, we have the weight down, and at equilibrium, these are the same. If there's no acceleration, they're equal. We get used to that. And so when you first saw this, you probably said, well, it should be the same acceleration because we're pulling on it with the same amount of force as the block was. But the tension in this wasn't the same. The other way to think about this is, let's see, where can I get some room? If you think about it from a system point of view, what is the system that's being moved? And if you put the 2 masses together in a system, so if originally we had 412 newtons and we had 908 newtons, and now we have 412 newtons and we're pulling down on it. How much total mass is there in the system? That's a lot, 1,320 newtons of mass. So, I just caught myself. Did you catch me? 1,320 newtons of weight. So W total, 1,320 newtons. What's the total weight here? Well, the total weight here is just 412. We went down by more than a third in the weight of the system. So if the weight of the whole system went down by about a third, I would expect my acceleration to go up. So weight went down, acceleration should go up, and we did. We went from 3.8 all the way up to 12. So went down by about a third, up by about a third. So that's another way to think about it, to make sense of why the acceleration changed. So did we answer the questions? Well, what's the acceleration of the lighter block? Part 1, 3.8 meters per second squared upwards. Part 2, what's the acceleration of the lighter block? 12 meters per second upwards. And then we figured out, why are they different? How can they be different when we both have 908 newtons on that side? So I hope this one made sense. It's kind of an interesting problem. The process you're going to take for any 2-object problem is going to be the same as this. You have to separate out the 2 force diagrams and then see if there's any connection between the two. If they're tied together, for instance, they'd better have the same acceleration. If they're tied together with a rope, that tension is the same. You might have other situations where they're connected with a spring or something else. So your job is to just make sure you understand, separate out object 1, separate out object 2, see what's connected, and then do our standard force problem. This is just the standard force problem process, and then we'll figure out how do we get to our answer. So I hope this one helped. Good job.